So, good evening everyone. We are glad to present you our project of air pollution forecasting sponsored by the European Space Agency and companies in Earth observation field as MEO, Sistema, IGEOS, Urbi and Orbit. So first, the main program of the European Space Agency in Earth observation is the ESA Sentinels. It's the guardian of the Earth. It consists in 6 missions combining different satellites to monitor Earth activities as land management, maritime surveillance, environmental disaster, and air pollution and atmospheric monitoring. What is interesting in this data is that it's totally open source. Everybody can use it, can have access to it, process it, analyze it. And the data we're going to be interested in is the Sentinel-5P data. Sentinel-5P is a satellite launched in 2017. It produces air pollution monitoring, air data about the atmosphere, and that's the data we used for our project. So the data that is used now for atmosphere monitoring is a numerical model based on ground measurement, but also satellite inputs. And as you can see on the image, it shows the concentration of NO2 all over Europe. So the bright pixels show more concentration of NO2. This data, it's 40 kilometer spatial resolution all over the world with the hourly temporal resolution. And what is really interesting in it is that it produces 5 days of forecasting. 5 days in the future, we can predict where will be the air pollution and what we can do for this. Sentinel-5P, here is an image of Sentinel-5P all over Europe. Same color map than the numerical model. And the characteristic of Sentinel-5P is that it produces 5 kilometer spatial resolution, so really high compared to what we have with the numerical model. And it's a daily global coverage. So by combining the information we can have from the different data and with the AI, we produce a solution, we produce a forecast of 5 kilometer with a forecast of 5 kilometer. And Luca will present you how we did it.
So we gather Sentinel-5P images, which are available daily, and we stack them into sequences of, let's say, 5 images. We then feed them to a deep learning model that learns to predict the next 5 images. To be more precise, we use an encoder-decoder network architecture, with the main building block being a convolutional LSTM. An LSTM is a neural network that is able to process sequential data. With this approach, there are 2 problems. The one is, as you can see, the satellite data from Sentinel-5 is incomplete due to cloud coverage and noise. The second problem is that the temporal dependencies are very complex and to some extent influenced by randomness. So in order to produce a forecast, we use additional data available from a simulation, from a numerical forecast, which is at a very low spatial resolution. We use B-cubic upsampling and then feed it to the decoder as an additional input. On this slide, you can see the results from our model. Down here, you can see the training loss and the validation performance, which increases heavily when we use additional data. We call this conditional Sentinel-5 forecasting. Up here in the top row, you can see the input, 5 Sentinel-5 images, and our prediction. In the bottom row, you can see an upsampled version of the numerical forecast. To wrap up, I think we provide some value here using deep learning by creating a model that is able to deal with this corrupted input data, which in the end produces a forecast that is slightly superior to the numerically computed forecast. Our team consists of Max, who has a background in remote sensing and who is working on environmental applications at MEO. Me, I've been working on computer vision, and I'm interested in applications of computer vision on satellite imagery. Our team is completed by Diego Valsesia, who is a PhD candidate at Politecnico Torino and a deep learning expert. We want to thank him for his very helpful insights during these 8 weeks, especially regarding network architecture and training. And we also want to thank our sponsors for giving us this great opportunity. Thank you.